Hello everyone, welcome to TriTea. Today we're going to solve two interesting problems, step by step. So let's begin with the first one.
Every programming language shares a core set of mathematical principles. Learning these patterns allows you to solve problems regardless of the specific software tools you use. A palindrome is a sequence that reads identically forwards and backwards. This applies to words like race car, but the same logic holds for numbers like 121 or 454. To build a program that identifies these numbers, we must translate this visual symmetry into a repeatable mathematical test. This algorithm consists of 3 stages. First, we reverse the original number. Second, we check the reversed version against the original. Finally, we output the result. Reversing a multi-digit number requires us to extract each digit one by one using a loop. However, processing a number in this way is destructive. As the loop peels away each digit, it reduces the original value to 0. To ensure we have something to compare our result against, we must store the original value in a temporary variable before the loop begins. The loop uses 3 arithmetic operations. We use modulo 10 to isolate the last digit, multiplication and addition to build the reverse total, and integer division to remove the process digit from the temporary value. Using 121 as our example, 121 modulo 10 gives us a remainder of 1. We add that to our total. Then, integer division by 10 removes that last digit, leaving our temporary value at 12. With the temporary value now at 12, consider the next iteration. Pause the video here and calculate the resulting values for the remainder, the total, and the temporary variable. In the second pass, 12 modulo 10 isolates the 2. We multiply our previous total of 1 by 10 and add the 2, bringing the new total to 12. Dividing our temporary value by 10 leaves us with 1. On the final pass, 1 modulo 10 gives a remainder of 1. Our total of 12 becomes 120 plus 1, resulting in 121. Dividing the temporary value of 1 by 10 reduces it to 0. Once the temporary variable reaches 0, the loop ends. The fully reversed number is now stored in our total variable. Now we can complete the final step, comparing the original number we saved earlier to the total we built in the loop. If the original number and the total match, the program identifies the input as a palindrome. This sequence, peeling with modulo, shifting the total, and chopping with division, is the standard method for reversing integers. This logic applies directly to production code. This Python script uses the same while loop and arithmetic operations we just used to process 121 manually.
Now let's see how the code looks in C. in Java. In Python. Let's now move to the second one.
Every programming language has its own grammar, but the underlying logic is universal. Whether you use Java, Python, or C, the goal is to solve the problem in your head before you ever type a single bracket. Take this pattern from a 1527 German manuscript. This is Pascal's triangle. It's an infinite, predictable mathematical structure that existed long before the first line of code was ever written. Constructing it is a visual process. It starts with a single one at the peak, which then cascades into a second row of two ones. These outside edges remain ones as the triangle grows. To find the interior numbers, you simply combine the two numbers directly above. 1 plus 1 gives us 2, centered on the third row. The pattern continues. 1 plus 2 is 3, 3 plus 3 is 6. As the rows increase, the internal values swell according to these simple additions. This visual intuition is our baseline. Before we can write an algorithm, we have to see exactly how the numbers relate to one another in physical space. Now we hit the machine's limitation. Computers don't see numbers merging in a vacuum. They process data in strict linear rows and columns. We solve this by snapping the triangle into a right-angle grid. Now we can identify every number by its coordinates: vertical rows, which we'll call I, and horizontal columns, which we'll call J. Our strategy is now a three-step algorithm. First, an outer loop to move through each row. Second, a formatting step to print the leading spaces. Third, an inner loop to print the values for each column. You might be tempted to use a 2D array to store the previous row just to calculate the current one, but that forces the computer to use extra memory to remember what it just did. Instead, we can look at the relationship between adjacent numbers within the same row. In row 4, the number 4 is 4 times larger than 1. The number 6 is 1.5 times larger than 4. There is a fractional relationship between these neighbors that we can express as a formula. The current value, multiplied by the row minus the column, divided by the column plus 1. Every row resets this process, starting with an initial value of 1 in the first column. Pause the video here and try it. Use this formula to manually generate the numbers for row 4 to see if the math holds up. By using this ratio to calculate values on the fly, we eliminate large memory arrays. We've turned a storage problem into a direct calculation. To prove this logic works in any language, let's look at the pseudocode. We've stripped away the specific syntax to focus on the pure logic and variable flow. We'll dry run row 3. Our outer loop, I, is 3, and our starting value is initialized to 1. At column 0, we print our 1. We then update our value using the formula. 1 times 3 minus 0, divided by 0 plus 1. Our val becomes 3. We move to column 1 and print the 3. Running the formula again, 3 times 3 minus 1, divided by 1 plus 1, shows our value is still 3. In column 2, we print the 3. The formula now calculates 3 times 3 minus 2, divided by 2 plus 1. The value returns to 1. Finally, at column 3, we print our last one. Since our column index has reached our row index, the inner loop terminates. This sequence of calculations is the same regardless of the language you choose. The tracker box doesn't care if you're using a print statement in Python or a printf in C. When you master the underlying algorithmic logic, you aren't just learning to code in one language.
Now let's see how the code looks in C. In Java, in Python, Comparing all three languages, C, Java, and Python, we can clearly see how the core logic is same in each three. Just syntax is the one which changes.
Every
Thank you for watching. See you in the next video.
Subscribe now.